So hello everyone, I am Baban and today I'll be discussing about SBM. So I'll just for wait 1 or 2 minutes to let others join. Okay, let's start. So today I'll discuss two things. So at first I'll discuss about SVM. So I think you have covered it in detail from the lectures, but I'll just give you some overview and then I'll go to practice questions. So let's start about SVM. So what is SVM? So this is a supervised learning algorithm which can be used for both classification and regression. And what does it do? It finds optimal hyperplane to separate classes. So this is for like classification by maximizing the margin. So if you see this example, there are many blue dots here. So this is one class, and there are many red dots here, which is kind of say another class. So what it tries to do is that try to maximize the distance between the two classes. And in regression, SVM predicts continuous values, and it optimizes hyperplane to minimize deviation from actual values. So whatever we are predicting, it tries to kind of uh, find a hyperplane to minimize the deviation from the say actual value and whatever the model is expected to predict. So why SPM? So SPM is applicable for both linear as well as non-linear classification tasks, and this is very like can be used for very wide range of real life problems. And then it is also very handy when we are using it for very large dimensions of data, and then it is very robust. So means like even if there are some say uh, some outliers, still it can handle it up to some extent, and it can also like generalize old unseen data, and it makes the model very reliable, and also like this has theoretical foundations. So like we can give some kind of proof that yeah, this will like it is expected to give a better performance like that. So I'll quickly go through basic intuitions. So here, suppose this is one class, this is another class. So what we are trying to do is that we're trying to find a plane, or here in this case you can say, because this is 2D, so just a line. And basically we want this line to be away both from this class as well as this class. So basically this one should be at the midpoint of both the classes. So because if you know, if this line is here, then distance will be more from here, but distance will be less from there. So that is why like if we choose the midpoint, then that means like it is equal distance from both the classes. So again this is like on 2D. So for so why do we need to kind of do this? Why not one line here, that is also fine, right? One line if it is here, that is also fine. One line if that is here, that can also classify, right? So why exactly do we need to keep it in the middle if all the lines can classify? So if these two are classes, and if all three lines can classify them, can separate them, why do we need to find something like in middle or something? So that is because okay, I'll explain that with an example. Okay, uh, this is a two dimension xy, but suppose consider it in one dimension. So here, this red indicates suppose the weight of a person. So this is the x-axis, and this suppose indicates weight of a person. And red means he is not obese, and green means he or she is obese. Okay, so and there can be a point where we separate this class from this class. So that point can be here, 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 anywhere. So where should we choose the point, right? So here, suppose we have chosen the point here in the the that color, orange color. So orange color, this one is suppose our dividing point. So anything left of that is not obese, and anything right of that is obese. So what will happen if there is some new point here? What it will predict? It will predict that it is not obese, right? Because this is the point is here. This point is here, and this point is right side of this point. So it will predict right side means obese. But is it really so? See, this point is very near to these points, all these points. So and these points are much far away. So does it make sense to put the point here? Because if this point is so much near to this, it makes sense to call this as not obese, right? Because these are so much away from this group. So basically, if we are able to choose this one, this orange one, the what we are what we are calling is that this is like if we are choosing it somewhere around here or here, then it will be able to classify them properly. Even though in the training data, suppose we are having these points only and these points only, but if we just blindly put it here, that will not be able to generalize well on the test set. So that is why we need to put it somewhere here. Similarly here also, uh, we need to put it somewhere in the middle, so that it is like distances, there is some kind of distance from this also and this also. So kind of we are trying to maximize the distance from both the classes, so that like we don't want to say put the point biased toward any class, something like that. So if you have any doubts till now, you can ask. You can just write in the chat box, or you can also unmute yourself and you can ask the question. So next, so what do we want to do is that we want to maximize the margin, and if we want to maximize the margin, so maybe somewhere here it would be the optimal point. Is there any question? Yeah. Okay. Concept of hyperplane. So can you? Okay. So here suppose there are multiple points here. There are multiple points here, and we are separating that via a point, right? So whenever you are separating it with maybe this is for 1D data, right? One dimensional. So whenever you do it for two dimensions, suppose here you are separating it. So this is a line. Whenever you are separating it for suppose 3 dimension, so uh, it will be like you have to separate it with say 2 dimension, right? So the separating thing will be 2 dimension. So that is the point here. So anything that is kind of a say that is even the point also, the point also can be called a hyperplane, but generally it is not. Generally we call maybe 2 or 3 dimensional things hyperplane, but this technically this is also a hyperplane. So anything that is used to separate and that has kind of say you can say that is linear, right? So maybe uh, you can consider you are in a room. So basically you want to divide the room by two parts. Maybe you can uh, give a say like say a mat. You can place the mat in the below the room. Maybe you can hang it around the room. So whatever it is separating the room perfectly, perfectly means it is kind of, it is just one dimension lesser than the what you are trying to divide. So that is hyperplane here. Is it not audible?
It's audible, sir.
Yeah. Okay. Okay. So here, so maybe if we just move the point here, then it will be fine, right? But what if there is some outlier? Suppose maybe if there are greens here and there are reds here and there are green here, and if we pick some middle, then it will be able to classify. But suppose there is someone who has very high weight, but he is not suffering from obesity. That is also possible. So this is one of the outlier. But if we blindly try to do this thing, that if we try to blindly put this line middle of these two classes, what will happen? This will be, the point will be here. Is it right? Because if there is some new point, okay, if there is some new point, what will happen? Suppose there is a point here coming, okay, then it will say it is not obvious, even though it is very near to all these classes, all these examples. So that is one of the drawback by doing this way, right? Because just because of one example, our margin is shifting from here to here. So that is the issue, and how to solve it? So in order to being drastically affected by outliers, what can you do? We can do one thing. We can call do it do soft margin, and in soft margin we can allow some kind of
Sir, in
constraint.
this figure, what is outlier? It's a green circle or red circle.
No, this
Which
one is
one
the
is
outlier.
outlier?
This one is the outlier. So here,
Orange.
yes, this orange. So all these are green, but only one here is red. So that is why this is outlier.
And one is green also. Sir, one is dark green also.
No, so you see
So
this example.
dark green is not outlier.
No, no. So green is near all the green classes, right? All the green points. This green is near those. So it is not loud. So red is supposed to be here, but red is actually here. So that is how it is outlier. Understood? So basically here, what we are seeing that green this green, like here we have only green points, here we have only red points, but here we see that there is a red point in the green side, so not where it should be. So that is why it is outlier, this one. So what you do expect, if there is some red, you would expect the red to be here somewhere, here near the reds, but this red is near to the green. So that is why it is not in its expected place. That is why it is called outlier. So is it clear? These two are not outlier. Okay, I'll discuss
Yes,
what it
sir.
is. Yeah. So these two are basically. So what we are doing here, we are allowing that, yeah, okay. So if we say that this point is the middle point, if we just ignore this and say this point is the middle point, and anything is in the right is green and anything in the left is red. So if we can do that, then that will be then we can classify the midpoint will not be here, midpoint will be here, but the issue is that it will say that this is green, right? So you have two problems. If you try to classify everything, then the margin is bad here, and if we try to kind of do good margin, then this will be misclassified. So generally, what we do, we kind of allow this to misclassify, so that even though it is not it is misclassifying some of the trend set, but it is classifying test set well, because you don't know that where the points in the test set will be. It can be anywhere. So suppose here, if the point is here and we are drawing the line here, and there are some points here in the test set, then it will say that it is not obvious, which will be wrong, because they may be like obvious. So they may be green, but the model will say no, they are red. So in the test set they will misclassify many things. So that is why we are allowing to, yeah, 1 point please misclassify it, but make sure that the margin is safe, margin is good. So
There's a lot of noise.
okay, so okay, 1 minute. So is it okay now? Are you
It's proper
Yes,
from
sir,
initial
it's
images, sir.
okay.
okay? Okay. Okay. Then let's move to the next slide. So what will happen if there are too many overlaps in the data? So suppose in this example, suppose you are considering how many, so you are taking medicine suppose, and how much medicine you are taking. So red here it means like suppose here it is 0, 1, 2, 3, 4 doses, and like maybe 8, 9, and here like maybe much more. So what will happen suppose uh, in those medicines, so I think my network is all right, yeah. So suppose in this case it is not separable. By that means suppose in this medicine what happens is if you take very low amount it will not help, if you take very high amount it will not help, but if you take just in between the dose what is given by the doctor, then maybe you will be get well. So can we draw a line here and classify? No. Can we draw a line here and classify? No. So you know this one is middle of this, so we cannot draw a line. We cannot say this if we something on the left will be this class, something on the right will be this class, right? So that is the issue. So this is not linearly separable because we cannot draw just a line here and say that left of this is this class, left of right of this is this class. So how to handle that? We can calculate this. So suppose we are taking medicines in this dose and it is not separable by default, right? So what can I do? We can take square of that. Square of that, it can be like cube of that, it can be any equation, right? Say for simplicity I have done it square, okay, here. So suppose it is 1 square, 2 square, 3 square, maybe it is 5 square, 6 square, like this, okay. So whatever is there we are just taking the square of it, okay. So the inputs, basic inputs are the same, but we are just basically transforming it to the higher dimension here, 2 dimension, just taking the x square. So what is happening here? If earlier there were no line that we can draw to separate these classes, if we want to draw one line and then we want to separate those classes, that is simply not possible here. We cannot draw here, we cannot draw here, we cannot draw anywhere. Wherever we draw there will be misclassifications, right? So suppose we are drawing it here and saying that everything in the right is green but these are red, right? So these will be misclassified. Same for here also, this will be misclassified, okay. So to avoid that we are moving it to the higher dimension and see these are the red here, these are the red here, and green is here. So we can draw a line like this, right? A straight line like this, and it will be able to separate this. So we can say that anything above this line is red, anything below this line is green. So anything above this line and they will like they will not feel healthy, but anything below this line they will get cured, they will be your medicine will work from them for them. So that is the thing here. So that is what SVM does. So it basically uh, tries to, if it is not separable by default, its convert is to the higher dimension and then tries to separate it. So I think the detailed things you can find it in the lecture. So I think in the lecture it is covered in the very much detailed manner. So this was the basic intention why we just do use SVM and why we need kernel functions to kind of a do kind of transform it into higher dimension. And basically we don't even convert it to higher dimension. So in the kernel trick, we just calculate what would be the separating hyperplane. Anyway, so and that is the basic intuition. If you have any question regarding this, you can ask. So after some time, we'll move to practice questions. Okay. How SVM ignores the outliers? So this is called like soft margin. So I think you can see it in the lectures. It is covered in the lectures. It is little bit difficult to say it in very a few lines. Yeah. So in the previous times, I basically solved the questions, but this time I will give you the questions. You will solve the question. You will write the answers in the chat box, and then I will discuss the answers. Okay. So this is the first question. So this is a question. So please think it yourself and write the answer in the chat box. What do you think and why do you think so? SVM cannot classify data that is not linearly separable, even if we transform it to a higher dimensional space. Yes or no? False, false, false. Okay. Yeah. Right. So this point, I think I discussed just now that if we are it is not separable, but when we are converting to higher dimension, we are able to separate it, right? But it is saying that it cannot be done. It is not linearly separable. But just in the previous slide, I have shown that yeah, it can be done. So this is false. Okay. So
Sir,
yeah.
you have converted your one dimension data into 2D. How
Uh, your voice is not audible clearly. So can you repeat?
uh,
Yeah. Can you repeat the
sir,
question? Yeah.
go to the previous slide.
Yeah.
Go to just the previous slide.
Yeah.
Just previous slide.
Yeah. Yeah.
Okay. Yeah, yeah. How this 2D dimension you will separate the linearly separable data? From where you will draw the line?
Okay. So if we draw a line from here to here, this is separable, right?
From where? From where?
From this point to
From
maybe this
where
point.
you will draw line?
From this point here. So line will be from suppose here, 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 like this.
So it is cutting the green dot, na? It is crossing the
Yeah,
green dot.
kind of.
So
So this is just for
how
example.
you will separate green and red?
Yeah. So this is just for
How you
example.
will separate green?
Yeah, yeah,
Huh?
yeah. I understood your point. So maybe here maybe line may not draw properly, but ideally it should. But even if it is not, then maybe convert it to third dimension. Maybe it then the distance will be much more. Okay. So maybe if it is not happening in second dimension, maybe take x cube.
So if this will not possible in second dimension, then we will go for the
Yeah,
third
yeah, yeah,
dimension.
sure. So in this
Then
case,
only I can then only I can linearly separate.
yeah. So here you can see it is not at all possible, right? Here
Hmm.
it is kind of possible, but maybe yeah, you are right. Maybe it will some part it will get overlapped, but it is much better situation than the previous one.
Oh, okay, okay.
Yeah, third
Okay, okay,
dimension
okay,
maybe it will be
okay.
much
Got
better.
it, got
Yeah,
it, got it.
yeah, yeah,
Yeah, got
yeah,
it. It will be more much clear in 3D,
yeah, yeah.
if not possible in 2D.
Yes,
Okay.
and also like this is just x square. Okay, we can use other function also, maybe 5x square, 10x square, whatever. Like there we have any possible combinations. Maybe x square plus x square minus x, whatever. We can use anything. So maybe in one of them it will be like clear. So this is the second question. Which of the following loss functions are convex? So at first 0 1 loss. So what do you think? It is convex or not convex? So this is the formula for 0 1 loss. 0 if y equal to fx. So if it is correct, if the output is correct as the gold label, so this is the say reference what is present in the label, and this is the model output. If it is same, then the loss is 0, and if it is different, then the loss is 1. Okay, so is it convex or is it not convex? What do you think? Write in the comment box. Using kernel is highly separable, sir. Can you clarify your question? I am not getting your question. Using kernel is separable. Yeah. In the previous example, if you use kernel, if you convert it to higher dimension, then it is separable. Yeah. Yes, kernel. So this question, what do you think should be the answer? Which of the following loss functions are convex? The first option is 0 1 loss. So is it convex or is it not convex? Okay, so when we say a function is convex, when it has one global minima, okay, and there is no local minima. And another way to find it is if we take second derivative with respect to the loss, then it will be like it should be 0 or it should be like positive. If it is negative, then it is like it is not convex. So in this case, we cannot take a derivative with a second order derivative of 0 1 loss. So here, like, we don't even have any second order derivative of 0 1 loss. So that is basically not a convex function. Okay. So in this is not this is not convex actually, because so if I'll show you a diagram that will be clear, much clear from that, but for now you understand that in this case there is no no second order derivative, but the condition is the second order derivative should be greater than or equal to 0. So that so first option is like this loss 0 if y equal to f of x and 1 equal to y not equal to f of x. So it doesn't have any second order derivative. If you take try to take a derivative of anything, you are unable to do. So I just wait a minute. I'll explore all the options and then I will show you a diagram, and I think it will be much more clear from that. Okay. So this is the first one. Second one is hinge loss. So again this is the function maximum of 0 and 1 minus fx y. Y is the label and fx is the output. So what will be like, is it convex, is it not convex? So hinge loss is this, and if we take the second derivative of hinge loss, it is kind of 0. Okay, second derivative is 0, and so that is why like it is also convex. So I think it may not be clear. I'll just show you a diagram. So logistic loss is also convex. Square loss is also convex. So I'm just showing the diagram here. So this is like 0 1 loss. Okay. And what do we need to do is that we need to find out if there is any global minima. So is there a global minima here? See here, where is this minimum? Here also it is 0, here also it is 0, here also it is 0, right? So global minimum is that there will be only one point where it is maybe 0, maybe anything, but it should be, lowest thing should be 1 point only, right? But it is not, it is multiple points, it is 0. So it is not convex. Another thing is that if you draw the line, suppose you are drawing a line between any 2 points here, maybe here to here, okay, it should be above this, okay. But suppose in the suppose exponential function, this is the diagram for exponential. Suppose you are drawing a line between this point and this point. This line is above the curve, right, above the curve. Same for this, if you draw a line from here to here, the line will be above the curve. Same for here, if you draw a line from here to here, the line will be on top of the line only, but not below. But if you draw a line from here to here, the line will be below the loss function, right. So that is also another way to find that it is not convex. So 0 1 loss is not convex, and all other losses here are convex. So is it clear from the diagram? So main point is like there should be a global minima, but here we don't have any global minima. This is also minimum, this is also minimum. Here you can see that it is decreasing, right. So at some point there will be some minimum. It is also decreasing. At this point is a minimum, right, for this one hinge loss. Here it is minimum. Here also at some point there is minimum, but here all these points are minimum. So there is no global minimum here. Yeah. So next question. So decision boundary obtained using Perceptron algorithm does not depend on the initial value of the weights. Is it true or false? So suppose you are classifying something, and maybe we are taking weight as 1 1 or maybe 2 2 or 0.5 whatever. It is trying to say that whatever we are taking, whatever weight we are taking, it doesn't matter. What boundary will be the same. Is it correct or is it incorrect? Any more answers? Okay, so anybody would like to explain why it is wrong? Maybe Ritika? Yeah. So okay. So in this thing, okay. So decision boundary, whatever maybe with Perceptron, what you are doing is that you are defining some initial weight, and then you are basically adding the misclass if something is misclassified, right. So that is basically dependent upon the weights. So whatever initial weights we are taking, if it is linearly separable, then we will get the results. We will get a classifier, a boundary, but the weights might be different. So suppose in this case, here suppose this is we are trying to classify with Perceptron. So maybe if we start with one weight, we will obtain this. If we start with another weight, we will obtain this. Another weight maybe obtain this. But it is not same like whatever we are starting, weight we are starting, the line will be this or line will be that. That is not possible. Depending upon the weights we are starting, it will be different. The separating hyperplane will be different. So that is what is saying here. So here it is like it is because the initial weights determine the direction in which algorithm starts searching for optimal decision boundary. So even though in all the cases, if it is linearly separable, the model will converge, but the initial weight might have defined boundary. So in the training set maybe it will be able to classify, but in the testing set maybe not, may or may not be, depending upon where the testing points are and where the boundary is. Okay, so this is interesting. Consider a linear SVM trained with n levels in R2 square, like R square, without slack penalties and resulting in K2 vectors, whatever. You have n greater than 100. So n is the number of points. Okay, so just ignore this. N is the number of points and k equal to 2. So k is the support vector. Okay, so you have maybe suppose 150 points and you are removing one data. Okay, 1 point, and then again training the classifier. So what can be the maximum possible number of support vectors? So you have n points, right? You remove one of them and you are training the model again. So what will be, how much support vectors we can take? Maybe we can take 2, yes, but maybe more, 2, 3, 4, 5, maybe n. How much we can take? I'm not saying that what should be the optimal. I'm saying that what you can take, no matter what is the result. Result, just ignore the result. Theoretically, how many points we can take as a support vector here? Anybody would like to answer it?
Can you please show the question again?
Yeah, sure. This is the question. So basically, ignore this. Consider that you have n points, and one of the point is removed. Now you want to perform SVM on it, and how many points you can choose as a support vector?
What is K exactly here?
K is the number of support vector in the like first operation with n, but k equal to actually number of classes you can consider.
N minus 1?
Yeah, n minus, yeah. Can you explain why? Just
Remove
try
one
to
data,
intuition, any intuition.
N minus 1.
Yeah. So here in the SVM there is no limit how much points you can take as a support vector. Okay, so there are total n points and one of them is removed. So you have now n minus 1 point. You can take one of them, two of them, whatever. Suppose in this example, maybe just not 1 point. You can take many points, this point and this point also as a support vector. Okay, so not that you have to choose the nearest one or anything. You can choose nearest one, nearest two, nearest three, maybe anything. Near all of them you can choose. But if you choose all of them, maybe the model will be overfitted. It will not be able to generalize on test data. But you can, if you want, you can choose all of them. So that is the point. You have n minus 1 points now, and you can choose all of them to be support vectors for your classifier. So answer is n minus 1. Okay. So you have an SVM kernel, and this is the k1 function. K1 means kernel 1, suppose. So it is x square, and you have k2, which is 3x square. Okay, so which of the following is true? So margin obtained will with k2 will be greater, margin obtained will with k2 will be smaller, and margin obtained with k2 will be the same as k1. Which of them is correct?
So it will be
Can you repeat? Hello? You are not clearly audible. Mhm.
Could you show the question again?
Yeah.
sir.
Mhm.
Option is C. C.
Why do you think so? Can you explain? Any intuition?
C and
You are not audible clearly actually. So the answer is not C. Okay. So I'll discuss the answer. Maybe think again. No, it is not C. So what are we doing here? In this function, we are taking just the x, we are transforming x to x and x square. But here, we are transforming to 3x and 3x square, right? So if you plot in the map, okay, so maybe there is point, 1 point, okay, maybe x equal to 1. So it will be 1 and it will be 1. And here it will be like 3 and it will be maybe, okay, let's take an example, okay. Let's take an example. Suppose x equal to 1, and what will happen if x equal to 2? So with first one, k1, k1 of x equal to will be how much? X and x square, right? So x will be 1, x square will be 1. 1 square is 1, right? x2, k1 of x will be, so this will be 2 and this will be 2 square, which is 4, right? Then go to k2. K2 is what? 3x and 3x square, right? So 3 into x is 1 here, so it is 3. 3x square, what is this? 3 into 1 into 1, right? So it is again 3. And here k2 equal to what? This is 2 into 3. You know, k2 is like a 3x. So 2 into 3 is 6, and then next one is that 3x square, I think. Yeah, 3x square. So what is that? 3 into x square. X square is 4. 4 into 3 is 12, right? So what would be the distance between them? First point and second point. First point is here, and second point is here. Okay, x equal to 1, x equal to 2. So for k1, distance is what? Two minus 1 whole square plus 4 minus 1 whole square and square root of that, right? If we find Euclidean distance, that is the formula, right? Okay. So this is for K1. What about K2? You take square root, then find the distance between this and this. 6 minus 3, which is, let's write 6 minus 3 whole square plus 12 minus 3 whole square. Let's find them. So this is what? Square root 2 minus 1 whole square is 2 minus 1 is 1, 1 whole square is 1 plus 4 minus 1, 4 minus 1 is 3, 3 whole square is like 9. So you want to find square root of 9. Let's find out square root of 9. Oh, sorry, square root of 9 is 3, right? Yeah. So the distance here is 3, right? Square root of square root of 10 we didn't need, right? Okay. Square root of 10. 3.1622. 3.1622. Okay. Here let's find out. So yeah, I'll discuss about that. So square root we are taking 6 minus 3 is 3, 3 square is 9 plus 12 minus 3 is 9, 9 square is 81. Okay. So square root of 90, square root of 90, what is that? Nine 9.48, 4868, whatever, equal to 9.4. So the same thing, if we calculate via K1, we are getting distance equal to this one, and if we calculate via the K2, we are getting distance is this one. So between every point the distance will be 3 times larger. You see 3.16, if we multiply by 3 it will be 9.48. So that is the thing. So if you use K2, every distance will be 3 times larger than K1. Okay. So if the distance between the points are itself larger, suppose in a suppose let's say in SVM, let me show a diagram with an example. So suppose this is the example, this is the image, and every distance is getting maybe multiplied by 3. So the distance between these and these will also get multiplied by 3, right? So maybe this will be shifted to here and this will be shifted to here, like that. The distance will be larger. So hyperplane will be also like the distance between this point and this point will also be multiplied by 3. So this distance, if we move it here, and this distance if we move it here, if we are calculating with h1 and if we are calculating with h2, the distance will, all the distances including the distances between the points, distances between this line and the point, everything will be 3 times more with h2. Okay. So that is why the first option is correct. The margin obtained using K2 will be larger than the margin obtained using K1. So is it clear to all of you? Can we say a straight line a convex function? Yes. So what happens in straight line is that suppose you have a graph here, you have a line maybe like this. So that has global minima. It has not any point where you can get stuck, any local minima or anything. So yeah, you can call that as convex function. So If you have any questions, please ask. Then I'll just wait some time for any question. Then I'll move on to the next question.
So in principal component analysis and LDA, we generally convert higher dimensional data to lower dimensional data to obtain a discriminant function. But in SVM, it's the opposite. We are converting lower dimensional data to higher dimensions to make it separable.
Yes. Right. Okay. Then I'll move to the next question. Yeah, so this is the answer. A is the answer. All the distances in K2 are 3 times the distance of K1. So this one is the correct answer. Yeah.
Hello, sir. What is the meaning of the margin here? What it represent?
Okay.
Margin.
So here, if you see, margin means the distance between the nearest point to the line. So this one is the margin. This one is the margin. Say, okay, I'll give another example here. You have the point here. Okay, you have the point here. This is the hyperplane here, optimal hyperplane, and this is the support vector, right? So the distance between the support vector and hyperplane is called margin.
Okay, understood.
Yeah. Yeah, margin is the distance actually. Yeah.
Sir, can you explain convex function once again?
Yeah. So convex function. Okay. Okay. Yeah. This one. So convex function means
Sir, with the help of diagram, you can search diagram from Google and then explain what is convex function. It will be better to understand us.
okay. I think the diagram in the that was also okay. So maybe you can take this example. Okay. So if you draw a line between any 2 points and the line is above the curve, then it is convex. So that means that the this one is actually above than this, and here you can see there is global minima. Okay, so maybe if you it is like y value is higher here and y value is lower here, so like at some point it will be the lowest, and it will not be like a
Sir, which one is global minima? Sir, which one is global minima in this diagram?
so
X or Y point?
y point, so it is minimum right here, it is the minimum, the lowest point.
Global minima.
Yes, global minima. So this is the
This
lowest point,
one.
right?
And what is local minima?
You are not audible properly. Can you repeat?
Sir, what is local minima?
Okay.
Local minima.
So local minima. Okay, I will give another example. So in this function, maybe it is not there, but consider this. Okay. so you have a suppose a function which is like this, sometimes it increases, sometimes it decreases, right? And global minima is what? This one, which is lowest point, right, in the whole thing. Then this one, suppose you are going to a hill, maybe you are traveling on a hill and you don't know that this point exists. Okay, maybe you are in an unknown area, you are traveling around and you are here. Okay, you are here, so you want to go to the lowest point. Okay, so if you come here, you will see that in the left also it is higher, in the right also it is higher, and you don't even know that this exists, global minima, right, because you are starting from here. So what we will think that in the both sides there are higher, here also higher, so maybe this is the minimum, you will think that, but actually this is not the actual minima, right? So local minima means at some point in the both side there are higher points and it is in the middle, like it is between it is some minima in. So in suppose if we consider this part, okay, suppose we are considering part of this function, only this part, then it is minimum here, right? But if we consider this as a whole, this is not the minimum. So in some local area this is the minimum, so that is why it is called local minima. But we want to find the global minima, so that is why the loss function will be the lowest. So is it clear? So maybe you can see here, like if
Okay, sir.
yeah,
Okay, okay, got it.
yeah,
Got it,
yeah,
got it.
yeah, okay. Okay, next question. Consider a Boolean function in 3 variables. It returns true if 2 or more variables are true. So basically you have 2 variables, maybe a, b, c, and all of them can take true or false. So if any 2 of them are true, then the function is true. If 3 of them is true, then also the function is true. But if only 1 or 0 of them are true, then it is false. So can this be implemented with perceptron? What do you think? So you know, perceptron can be implemented if it is linearly separable. So do you think this function is linearly separable? Yes or no? Think and give me the answer. So any answers? Yes, but why? Maybe. So if you can see XOR function, it is not separable linearly, right? So let me draw XOR function. So you know, this is the XOR function, right? So this is also not linearly separable, but why is this linearly separable? Maybe any intuition you can show? It is correct, yeah, it is linearly separable, but I'll just show the graph here, to you. Okay, so in the next slide there's a graph. So I have drawn what can be the points. So it is that okay, let's just write it. Okay, so let's just do it here. Okay, so maybe this is first variable, second variable, third variable, and this is output y. This can be let's do like binary thing. Okay, true, false, true, false, true, false, true, false, true, true, false, false. So what would be the output here? All three are true, so it will be true. Two of them are true, so it will also be true. Okay. Again here two of them is true, so it will be true. Only one of them is true, so it is false.
False.
Yeah. Two of them are true.
XOR operation you are applying, sir.
No. So this is the question.
Sir,
right?
you are applying XOR operation, na?
No. This is not the operation. So operation I'll write. True if two or more inputs are true. So
Else false.
else false. Yeah. So this is the heading here. So here three of them are true, so I am writing true. Two of them are true, writing true. Two of them are true, again true. Only one of them is true, so it is false. Similarly here, two of them are true, so it is true. Only one of them is true, so it is false. Here also only one, so false. Here none of them are true, so again also it is false. So suppose we consider false as 0 and true as 1. Okay, then let's plot a graph. Okay, so that will be the graph. So here this means false and here it means like true. Okay, and there is another dimension. This is basically a 3D graph. So perpendicular, and that is like another dimension, true false. Below is false, up is true. Okay, so what are we doing here is that suppose this point is, this is like 0 and yeah, so if we consider from this point, this is 0. Okay, yeah, so you see that these four are the points. So if we just plot the points here, and if we consider this as like 0 and 1, so these are the points. So here the green means it is true and red means it is false. Okay, and this is basically this is actually a cube, so this is in the like upper outer part of the cube. Okay, so you can consider this as a kind of a cube, this is another plane, and this like that, and this is in the like outer this one, outer edge, outer vertex. Okay, so we have kind of 8 vertex, 4 of them are true, 4 of them are false. So can we separate them by a linear plane, like any, suppose if you consider this as a say cube, can we cover this, can you separate these classes with say kind of a sheet of paper. So these all these are actually linearly separable, so because if we kind of try to draw a plane here, it is possible to keep keep this green part and keep the red part separate. So this is actually linearly separable. So otherwise you can think of that also. So suppose the function is it will return true if it is more than 0. Okay, so you can consider this. So maybe x1 is 1 x2 is 1, x3 is also 1, and maybe beta like b is maybe minus 2. So what we will do, x1 into a plus x2 into b plus x3 into c minus 2, and we are seeing a threshold, maybe if it is greater than 0 then it is true, otherwise false, right? So what will happen if we give two inputs, maybe if any two of them are positive, if even any two of them are 1, so it will be 1 1, and here it will be minus 2, so it will be 0, so then it is true. If there are three positives, it will be 3 minus 2, so 1 will be greater than 0, so it will be true. But if we give less than 1, maybe there are no ones, 0 0 0 minus 2, it will be lesser than 0, so that will be false. So that is actually can be done by bisector, because it is linearly separable. We can draw a plane here and we can separate the green and the like red points. So is it clear? Yeah. So the
Not
next,
clear.
yeah.
Not clear. What's the answer? Is it linearly separable?
Yes, it is linearly separable, because you can draw a plane here and you can separate the green and red lines. So red means false and green means true.
What are the green and red points actually?
Okay, so here you can see we have taken three inputs A, B, C, and here
Clear?
here.
Okay.
So
The truth table is clear.
yes, truth table is clear. So we are considering t means 1 and f means 0. Okay, and we are plotting the graph in those dimensions. Okay.
You're plotting only like 3 red points. Then
There are 4 red ones, right? 1, 2, 3, and here. 4.
okay.
Yeah, green also here is 1, 4. So it is in the corner, that corner of the cube, other corner.
Okay.
And this
Then
is,
how you plot this graph?
so if we can, it is difficult to show in the 3D, but maybe if you, this is in the suppose below that side. So if you take a plane here and draw it till this below that, so from this is the top, and from this diagonal to below that diagonal, if you draw, then that will be like both separated, right? Because you have to consider that this is like in the corner, and this is also in front corner in the of a cube. So then you can separate. If you draw a line on top of it, before before the diagonal, on top of the diagonal, if you draw a line, and if you take the diagonal to the bottom of this, then you can get like both of them separate.
Sir, can you please explain from the truth table how you draw this graph?
Okay, so we are considering this as suppose x1, this one may be x2, and this one is suppose x3. Okay, and suppose here, okay, this is 0. So suppose x1 here, x1 is 0 here. Okay, and then we have x2, x2 is also 0 here. Okay, and x3 is also 0 here. So in this point, all of them are 0, right? So that is red. Red means it is false. So here 0, it is also perpendicularly y-axis, like this one is also 0 and this is also 0. no, this one is 1. So suppose you are considering here, suppose yeah, like this. So consider this, like x2 you can consider here also, okay, so it doesn't matter. So what I am saying is at this point, in this case x1 is 0, x2 is 0, x3 is 0, so it is 0, it is like false in
No,
this.
sir, x3 is 1. It is 0, 0, 1. 2 f's, 2 times false and 1 true.
Here,
So that's why everything is false.
yeah, I am saying in this point it is
Yeah, sir, 0, 0, 1.
why it is 1,
Because one coordinate is having 1 unit.
which
Because
coordinate?
0, 0, 0 will be at the corner most one, na? Middle corner.
No, which coordinate here is 0, 1?
Sir, suppose this is x1, x2 will be 1 here.
No. So x2 here you can see, if you consider this line here also, this is 0, this is 0 0.2, 0, 0 0.3, 0 0.4, 0 0.8, this is the one, okay.
Okay, okay, yeah.
So
We
in
can
the,
consider this also, but
yeah,
x-axis, y-axis and z-axis, if you are considering that, then on the middle corner will be origin.
yeah,
Yes, sir. So from the origin, we will go towards x1, then towards y1, and then towards x, suppose x, y, and z. Suppose these are the 3 coordinates,
yeah,
like that.
yeah. So but in this case it is drawn like this way, it is, this is the origin, it is drawn like this, so you can understand
Okay,
that everything is 0 at this point, right? So
okay, sir. Okay.
so this is 0 0 0 and 0 0 0 is false, it is red. This is 1 0 0, 1 0 0 is
Yes,
also red. This is
right.
1, but
0, 1, 0. This is
yeah,
0, 1, 0.
yeah, 0 1 0.
This is also false.
No, this is, yeah,
And
0 1 0, right, this is also false.
yeah,
This is 0
0,
0
0,
1,
1.
so
0,
this is
1.
also false, but these are
Right.
like others, so they are true and we can separate them. So is it clear to everyone?
Yes, sir. Sir, this is also a statement during the algorithms. We have studied that any linear equation, any linear graph is always points there are linearly separable. If it is quadratic like x1 whole square plus y1 plus z1, then it will not be.
Yes,
So here only 3 variables have been used, a, b, and c, and that two linearly, so they are linearly separable.
yeah, right.
Thank you, sir.
So I'll move on to the next question now.
Sir, I wanted to ask that whatever you have explained right now,
Yeah.
if these questions come in exam, so I mean, if these questions come, so I mean, what exactly we have to do? Do we have to take such truth table and do all the points plotting, or
No, no,
what should
it
be
will
the
be MCQ
approach?
type. Exam is always MCQ type,
Okay,
ma'am.
okay, okay, okay.
So maybe for finding the answer, whatever you can write in the paper to draw a diagram or anything, but yeah, the final answer you have to write, so, like MCQ. To find that if it is correct or not, if it is like linearly separable, you may like to draw, you may not draw, based on whatever method. To find the answer, you can like draw or not draw, but you don't have to like write this in the exam sheet, like in the answer sheet. Okay,
Yes.
this is for like I have done to make it easier for you to understand. Just it. So this is another question. So let x be an input instance, and so xi be an input instance with label yi, and this is the equation yi multiplied by beta 0 plus x transpose I beta 1, it is greater than 0. Okay, so which of them is correct? So you have a SVM and you have a input, and the input satisfies this equation. Okay, input and this is the label, and that input and label satisfies this equation. So what can you say about that input? that example? What is it? Is it a support vector? Is it not a support vector? It can be like both. What? So this one is covered in the class. So suppose this is the your support vector machine. What happens is that for this equation, for that equation, this one is equal to 0. Here it is greater than 1. Here it is less than minus 1. Okay, that's what happens. So for this point, it will be equal to 1, and whatever, like for the support vector it is equal to 1, and for anything like after that it will be greater than 1. Okay, so in this equation okay, so in this equation how to find the support vectors? yi into beta 0 plus xit beta 1 equal to 0. If it is equal to 0, then it is support vector, but it is not equal to 0, it is greater than 1. Okay, so if it is greater than 1, that means it is not support vector, it is outside. Okay, so we can say this. So in this example, okay, so this example, equal to 1 is this, equal to 0 is anywhere on the line, equal to minus 1 equal to is this, and anything that is not greater than 1, okay, that is like outside that support vector. This
What
is not a
is
support
on
vector.
the dotted line close to the blue points, that support vector close to the blue points, it is less than equal to minus 1. No? What is the equation on that line? What is the
This
equation
one,
on that line?
it is
Yeah.
equal to minus 1 on the line.
Equal to minus 1 on the line and less than minus 1 beyond that
Yes,
line.
yes, right. So here you can see more than plus 1, 1, between 0 and 1, between 0 and minus
Excuse me,
1.
sir.
Yeah.
Sir, if Arun sir don't mind, can he please turn off his mic?
Which one? Okay, I'm looking at it.
Okay, sir. Okay, I forgot. Okay.
Thank you, sir. Thank you.
So you know, this is like more than 1. This is 1, 0 to 1, 0, 0 to minus 1. Line is the minus 1, and it is less than minus 1. So if we are saying that this is greater than 1, that means it is kind of here. So here it is not a support vector, because support vector is equal to 1 or equal to minus 1, not greater than 1. So first point we cannot say that yeah, this is not a support vector, right? This is a support vector, we cannot say this is not a support vector. Yeah, we can say that x is either outlier or support vector. So we are saying that x must be either outlier or support vector. So that is not really correct. It can be outlier, but it cannot be support vector, right? Because we decided that support vector is equal to 1. So we are saying that depending upon situation, it can be outlier or it can be support vector. But we have shown that whatever the situation is, it cannot be a support vector. So this is also wrong, third option. And this is also saying that this may or may not be support vector depending upon other point. So that is also not correct, because if it is greater than 1, it is not a support vector at all. And also similarly for like any other point, if it is equal to 1, it is support vector. If equal to minus 1, it is also support vector, but anything other than that, it is not a support vector. So I think it is clear. Suppose we use linear SVM to build a classifier for 2-class problem. So basically whatever we have shown in the diagram, so we are doing mostly 2-class only, and will the classifier trained in this manner always be same as the classifier using perceptron learning algorithm? So suppose I am showing something. Let's show it a diagram. Okay, so this is the suppose SVM. Okay, this is the SVM. This is the line we have obtained using SVM. The question is, suppose we are using perceptron training algorithm, so they are linearly separable. So the question is, will the line, the separating line will be the same as this? What is the answer?
Can you just show the question?
Yeah. You are using an SVM, and another one is that you are using a perceptron training algorithm, and will the classifying line be the same in both the algorithms? So many have answered yes. Okay, the answer is wrong. See, in this case, yeah. So in the perceptron learning algorithm, what can happen depending upon the initial parameters, we can get this line, this line, this line, any line we can get. We will be able to separate, but we may or may not get this line, right? So in the SVM, we know that we will get a line which is like equal distance from this, equal distance from this, but in the SVM it is not guaranteed. It can be any line. It will be like, considering, if we, in this example, if we consider in say perceptron training algorithm, it can be like this line also, this line, anything, any line can be there. Okay, so they will not be the same. So that is actually one of the point, because that we use SVM, because if that were not the case, then we would have just used the PTA, perceptron training algorithm. That is the one of the drawback of perceptron training algorithm, and that is one of the reason that we use SVM. Not the only reason, but yeah, one of the reason.
Drawback of perceptron training algorithm is that
You can have, say, you here suppose this is one class, this is also another class. Okay, so you can, it can have this line, that line, anything can be there. Okay, so depending upon that, depending upon where that your training data is, the classifier can misbehave, or depending upon where the initial weight parameters are. Okay, so you know, in case of SVM, we are getting that we have a distance. It is like actually some distance away from this point, some distance away from this point, and it is actually in middle between both the classes. But if in the say in the PTA, if we can draw a line here, suppose here we are drawing a line, okay, then also it is valid, because it is able to classify this and this, right? But is that really good? Because new point may come here, and if we are drawing line here, then we are saying, we will say that new point is red, even though it is closer to green. So that is why it is drawback of perceptron training algorithm.
okay.
Yeah. So next question. Which of the following are true regarding SVM? So let's go point by point. First point, true or false. So for 2D data point, the separating hyperplane plane will be a straight line. Is it true or false?
Yes, sir. True.
Yeah. Any more? Anyone else want to answer? No. So I think like this is very clear. You have seen in the example only. This is 2 dimension, you know, and this is feature x, this is feature y, and then you are when you are trying to separate it, it is a line. Okay. So whatever you remember, say suppose there are n dimensional input, then the hyperplane will be n minus 1. So for I have shown in the example in this point here, this is 1 dimensional, so the hyperplane is like 0 dimensional. So here the hyperplane is like just a point. Okay. So for understanding, I have drawn a line here, but basically it is just a point here. Anything left of that is red, anything right of that is green. Okay. And for 2D, the hyperplane is 1 dimensional, 1 dimensional is just a line, and then similarly for 3D, it will be like 2 dimensional. So that one is correct. Let's go to the next point. Okay, next point. In theory, Gaussian kernel SVM can model any complex separative hyperplane. So what are you trying to say is that the SVM can actually, even if the function is complex, the separating function, if the classes are maybe much overlapping, also like it can do, if we convert it to higher dimension somehow, at some point of time it will be able to separate. So is it correct? So this is actually correct. So if the in this case, whenever like if it is not linearly separable, we'll forward it to like we'll transform it to higher dimension and so on. And also there is something in RBF like we can do infinite number of like say dimensions. Okay, like that is I think covered in the lecture, but theoretically it is possible that whatever the complex how much complex a function is, doesn't matter, we will be able to separate it theoretically. Okay, so this is also correct. Next one, for every kernel function used in SVM, one can obtain equivalent cost from a basis expansion. So is it correct? So this is also covered in the lecture, I guess. So yeah, it is covered. So basically there are in some cases like there can be a case that not all the kernel functions can be like we can convert it to equivalent basis expansion. So here you can see basis expansion I have shown here, that this is the basis expansion function, okay, k1, k2, but not all of them can be like written like that. So yeah. Then another thing is that overfitting in an SVM is a function of number of support vectors. So what you are saying is that in an support vector machine, if we increase the number of support vectors, overfitting might also increase, or maybe the opposite, if we are increasing the number of support vectors, overfitting might decrease. So is there a relation between that? So if we increase or decrease the support vectors, then the chances of say overfitting will also decrease or increase. Is there any relationship?
Sir, I think there is relationship with training data and overfitting.
Yeah, so suppose there are 10 training data, okay, and suppose we are taking two support vectors, or we are taking 10 support vectors, which is more likely to overfit? Training data is same for both the cases. Suppose 10
10
examples.
support vectors.
When we are taking two only, then I think result will be better.
Yeah. So what is happening is that if we try to take all of them, or all in the training data, it will be able to classify all the training data very well, but it will not do well on the test data. So
Right.
that is why, like, it is we can say that this is overfitting, because if we considering the hyperplane, separating hyperplane from using all the data, obviously it will be able to do on those data, but outside of that, not really. Okay, so next question.
So it's true.
Yeah,
Yeah,
so it
yes,
is true.
Sir, if we increase the number of features, what will happen to this SVM? Is it increase its bias?
Number of features means number of examples, or number of what do you mean by that?
Number of features.
Okay, so you mean, so suppose you have a point here. Okay, suppose on this point, by number of features you mean number of examples, like instead of 8 you are taking 20, or do you mean that this has more dimensions?
So no, she's saying about dimensions x1,
Oh, more
y1.
dimension.
Yeah,
Okay, okay,
like x1, x2, x3, and x4. It is like that.
yeah,
She's saying like that.
yeah. So again, yeah, if you take more dimension, that means it have much higher information, right? So maybe if you are taking 2 dimension, then 3, then it has higher yeah, it has higher information, more information. And if it is having more information, it is possible that model might find a pattern between the extra information. Maybe suppose let's say, uh, let's give an example. You are okay, so you are, let's take an example, how much you are studying is one feature. Then another feature is that uh, how much marks you got in the assignment, second feature. And third feature is did you see the movie, some movie, suppose Avengers. Okay, third feature. And output is did you pass or fail. Okay, so first two feature I think is sufficient for classifying if you can pass or fail. Okay, but it is possible that uh, in the training data there are 5 people who watched the Avengers movie and all of them passed. So they are not really related, right? They are just coincidence. But what will happen? Model will consider that as a they are correlated. So if you watch Avenger movie, you will pass the exam. So, but maybe in the test set they are not really correlated, right? It doesn't mean that if you watch a movie you will pass. So in the test set, if someone is watching Avenger movie, it will say you will pass. Doesn't matter like the how much hours you are studying, or how much you are passing, how much you are getting in the assignment. So that is also kind of creating a overfitting situation, because uh, they are like correlated, but that is not really a cause. Like in the training data, there is a correlation that you are if this is happening, if you are watching Avengers, then you are passing, but it is not really the reason of passing. They are just like coincidence. So again, if you use more feature, this kind of things are more likely to happen, and that can cause overfitting.
Sir, if that feature also used to improve the output.
Yeah, then it is like less likely to happen, but again the chances are higher, right?
Okay, sir.
Yeah. So like if the model has more information about the data, so it will be able to kind of a try to find a pattern so that it can feed the training data. So suppose you can say, let's say this example, okay. So okay, so let's think it this way. So you have a training data, okay, and suppose something is not correlated, okay. So in that case, a model will not be able to find a pattern and it will not be overfit, okay. So suppose there are two dimensions, it will not be able to find any correlation in that two dimension and it will not be able to overfit. But in just when you are coming to third dimension, so just when you are coming to third dimension, it is somewhat more likely. So you can think, so it can overfit in one dimension only, two dimension also, third dimension also. But whenever we are going higher, it is the chances are much higher, because in each of the direction, each of the dimension, we have some chances of overfitting. So this is the next question. So this is the green points and this is the red points. So if we remove one point, just one point, so that will change this line. Which point can we change to change this line? So if we remove this point, will that change the line? If we use this point, will this change the classifying line? What is the answer?
The red dot. Red dot.
So the point which is closer to this support vector.
Right. So yeah, this is very easy. So if we just remove this here, then it will be like this, because near should be this and near should be this. So this point will be that. Okay. So yeah. Next question. So after training, if we discard all the examples, so suppose in the just previous example, after training is done, if we just remove all the examples, all this other than the support vectors, so we will just keep this and this and just remove all this. So will that still work?
Sir, please, can you ask question again?
Yeah. So you are training an SPM, and suppose this is the SPM here, okay, and
Yep.
you are removing this one. So this is support vector, this is support vector, and everything else you are removing, okay. So
Yes, sir.
can you still classify with these two, like this line and
Yes,
this
sir,
one?
because it is classifying both the things, we can say, to two different groups.
Yeah. So this is the point here. So basically in SPM, you got the line, the like hyperplane, separating hyperplane, you got the support vector, and like these two are actually required to classify, because here maybe this is like -1, less than -1, and this is equal to -1, like there will be a parallel line to this, so that line will be -1, this line will be 0, this line will be 1, and here it will be like greater than 1. So any point, if you see it is coming after this point, it will be still able to say that yeah, this is 1, and any point this is coming, and say this is -1. Okay. So that is the point, that just if you consider this and the hyperplane, then you can just classify. Hyperplane you can just obtain with this and this, right? So that is the thing. You will be able to classify even if you remove all of them except the support vectors. Okay. So the answer is true. So even if we discard all the examples, it will not affect classification, as decision boundary is determined solely by the support vectors. Okay. Okay, so this one is little bit complicated to look, but not really hard. Okay, so you are plotting visualization for different values of gamma, so which is a kernel coefficient, and for some reason, like you forgot to tag which one is which. like so these three you have, okay, and you don't know which gamma value is which, okay, so which one is greater than which you don't know. So what can you say? Where is the gamma value highest and where is the gamma value lowest?
Lady teacher's voice is going on in the background.
Yeah, someone.
Sir, from background, some voice is coming.
Yeah. So someone is using the same room in the lab. Okay. Can you understand the question? Is it clear?
Yes, sir, it is clear.
Okay.
No, the question is not clear for me. Can you please say?
Okay. So in this question, we are asking that if there are like three diagrams and with they
If you
have
show the diagram, it will be better, I think.
yeah.
To show the question.
So we have three diagrams here, okay, and we want to ask that in which of the diagram the gamma value is the highest. So maybe let me make it large, okay. So the question is in which of the diagram the gamma value is the highest and in which it is lowest, or is it equal? So which of the options are correct? So
Gamma
this
value means what?
so gamma
Gamma
value
value
is like
means what?
Carnot coefficient for SBM. So this is one is G2, G1, G2, G3.
Sir, how to identify the gamma value, sir?
Okay.
And
So
which one is the gamma?
yeah, I'm telling that. So gamma, the like meaning of gamma value is covered in the lecture. Basically what happens, if you see the gamma value to a higher number, it will overfit, and if you set the gamma to lower, to it will like not fit very well. So in this case you can see the blue class, it is overfitting, you know, the boundary, it is very near to every point, it is not covered here, it is outlier, still it is classifying correctly, right? So this means it is overfitting. Red also, you know, it is a very classifying boundary. If you see here blue or blue, red is like red, so everything, the boundary is very near to the to the examples, and it is also classifying on the outliers. So that means it is getting overfitted. So maybe what will happen if there is a new point here? In that case, it will say it is blue, but is that so? It is very near to the red. Blue is much away, but still it will give blue. So that is a symptom of overfitting. To kind of classify this correctly, it is kind of a forcefully marking it as a blue. It is also like considering this as a blue. So this is, that means like the gamma value is very high here. So that is why it is overfitting. Here also not as much as this, but you can see the decision boundary, these are very much overfitting, right? It is much near to the points, but here you can see the boundaries are much more smooth here, here it is like brown, here it is red, here it is like yellow, here it is blue. It is much more smoother than all this. So it is overfitting the most.
G1 greater than G2 greater than G3. Sorry, G1 less than G2 less than G3. Is it like that, sir?
Yes. So here it is overfitting the most. So that is why G3 is the highest. It is overfitting the least. So G1 is the lowest, and it is in the middle. So this is between them. So that will be the correct. G3 is the highest, G1 is the lowest, and G2 is in the middle. So
sir, that means gamma value is giving us accurateness of the classification. Is it like that?
no. So like there is an equation for kernel function where you use the gamma, how much you want to kind of bring those together. Okay, so here like if you give the gamma higher, then it will try to kind of forcefully try to kind of classify it, even if it is overfitting. Okay, so like there is some spot and you have to kind of decide that what could be the better place such that it is not underfitting, or like it is able to generalize properly and also not overfitting. So yeah, so in the lecture it is covered. So week 4 you can see that here, kernel coefficient.
Thank you, sir.
Then this is a support vector. Okay, and we have alpha, we have a support vector, and we have the output. Okay, so you have to find the coefficient of the linear separator. How to do this? So I think it is covered in the class, but I don't think you have done the numerical on it, so I'll show. So this is the formula to find the coefficient of linear separator. Okay, so what is this? Alpha I and xi yi. Okay, so let's take the first point. What is the alpha I? Alpha is 1 into support vector is 1 2 1 1 2 1 1 2 I have taken into y 1. Similarly for xi 0.5 into this line 3 3 4 and into 1 1 minus 1 1 1 and minus 1. Okay, so let's multiply 1 into 1 into this is this only, 0.5 into this into 1 is 1.5 1.5 and 2, and minus 1 is 1, minus 1 into 1 is minus 1, and minus 1 into 1 is minus 1. So if you add all of them, 1 plus 1.5 is 2.5 plus 1 3.5. Okay, 1 plus 1.5 is 2.5 minus 1 is 1.5, 2 plus 2 is 4 minus 1 is 3. So this is the coefficient. Okay, then suppose we have 4
Show the previous question.
Yeah.
Question.
Yeah.
No, not that the question.
This question?
No. The next one. Next question.
Yeah, this question.
Yeah, that doesn't have the question, right? Just go the previous slide.
Yeah.
Yeah, that one.
Yeah. That is the answer for that question, for this question. So you have alpha values of this. Okay, sorry. So okay, this one is like 0.5 there and 0.5 here. So yeah, it is written wrong. Thank you for pointing out. Yeah, this is 0.5 and this is.
Sir, how you will calculate 3.5?
Okay.
3.5. How did you calculate 3.5, sir?
So up to this, is it clear?
Yeah.
Yeah. So
This line is clear.
you just do element wise addition. 1 plus 1.5 plus 1.
1.5, 2.5. Okay.
Yeah.
1, 1, 2. Okay. 1. Okay.
Yeah.
Again, could you please show that question? I just want to take
suppose
an SVM following Lagrange multipliers and support vectors. Compute the coefficients of the linear separator. Support. So y is support vector.
Mm-hmm.
Okay, thank you.
So we have 4 training examples. Suppose x1 is 0 0 and x2 is 2 2. Okay, and these are like a positive class, like output is 1, label is 1, and negative example is h equal to 1, like h and 1. So x equal to h, x1 equal to h, and x2 equal to, let's suppose like just consider 2 dimension. First dimension is h and second dimension is 1. Okay, and x4 is like 0 3. So what can be the value of h? so that we can still separate. So you can try to draw it on a paper or anything to find the value of each. Can you find out? What do you think should be the value of each? So you have this point in one class, these 2 points in one class. What can be the value of each so they are separable?
Could you please show the answer in the previous question?
Yeah.
Previous question.
Yeah.
Okay, that answer is 3.5, 1.5, 3. Okay.
Yeah. So let me show you the graph. This is the graph, okay, for these 2 points. 0, 0 and 2, 2, they are one class, and h1 and 0, 3. Okay.
Sir,
Yeah.
can we make their slopes equal so that to find the value of h, y2 minus y1 is equal to x2 minus x1?
Yeah, you can try.
So
Okay. Yeah. So in this case, suppose h is the point, and so what could be the value of h? So it can be here, y equal to 1 here, right? And this dimension is 1.
yes,
This
yes.
dimension, what can be the value? So still that we can separate red points from blue points.
Sir, H1 will be left side from their original position. Then only we can separate
Original position meaning?
where it is placed H1, and if we will shift left side from that position, so we can separate.
So suppose we are drawing a line here like this, okay? We can separate, right? Red points are above, blue points are below.
Yes, sir.
So
Yes, sir.
shifting left, yeah, you can do. But the question is what can
Little bit.
the question is
Little bit. We can.
the question is what can be the highest value of h. So if we take the h here, then we cannot classify, right? Because then
So I think so the point joining the blue, the line which will be formed by joining the blue point and the orange point. So we have to keep the slope of that slope minimum from that line, right? That would be the condition, right?
not really. So our answer is kind of really easy here. Suppose you want to classify, you have to kind of draw a line between this class and this class, right? So you can draw a line here, okay, just above like this, okay, right?
Sir, the value could be 1 in place of H1. That could be 1 1. So we can separate. So
No.
1 1 or 0.9, 0.8, something like that.
Yeah. So it cannot be 1, it can be less than 1. Just 999, it is also fine.
Yeah, it can be less than 1. It could be 0.9 or 0.8.
So the point is that suppose we are moving this to here at 1 1, what will happen? We will not be able to draw a line. Suppose if we draw, here is the point. Suppose you imagine the point is here, and then if we draw a line, we will not be able to classify. In this case, like this point will be below, the blue point will be upper, so we cannot really separate between them. But if the point is somewhere here, okay, here, then also we can draw a line just here, so that we can just above that on this point, okay. So anything above is say red, and anything by below is like anything below is blue. So this point can be here, but if the point is here, we cannot draw because it will be on the line. If the point is here also, we cannot draw because if we draw, then this point h, suppose we are saying 3, 1, okay. So the point is here. Suppose if we draw a line, then like this will be misclassified, right? Because this will not be at another side of the line. Both blue will be so blue should be on one side and red should be on another side. But if we move the line more than 1 or near to 1, it will not be possible. So that is why like a maximum value of h can be near to 0 but not really 0, because 1 near to 1 but not really 1, because if it is 1 it will be on the line. So we will not be able to classify even there. So very near to 1 it is okay. So answer is that up to h equal to 1 but not h equal to 1. So is it clear?
Actually, could you just explain why these 2 points are red and the other 2 points are blue plus?
Okay.
2 points are red circles.
So these are assuming that these are given in the
So,
data set.
sir, show the question. Sir, show the question.
So in the
Please.
question it is written positive examples
Hold.
this and negative examples are this. Okay. So positive examples, say these two are positive examples, so we have marked in this color, and these two are the negative examples, we have marked in red color. That's it.
And how did you get that h? Okay, 0 less than equal to h less than 3.
Yeah. So like we can separate by drawing a line here, right? So if the h is this point is left of that line, then it can be classified, right? So if we draw a line here, it will pass to 1 1, right? So
Yeah.
it can be left of that, so it should be less than 1. But if it is like, yeah,
What if it was like something like 1.51?
so
What if h was h had coordinates?
suppose you are taking here, suppose 1.51,
Yeah.
okay, so you cannot draw a line to separate red points from blue points, right? So you cannot build a classifier, linear classifier. So
Yeah, still there can be a line, right, passing from the origin and
what?
3
But
or
if
3 or
it is
1.
passing from origin, then it will include blue point also.
Yeah.
So definitely we are supposed to go below 1, 1. We need to construct a line which separates the blue group and the red
Yeah,
group.
right. So if
This
you,
is the
Okay.
question. Now.
if there is a point here, you will not be able to, you can draw a line, but in the below of the line there will be blue points but also red point, but we want red point one side, blue point on another side. That will not be possible.
Okay.
So this is the last question. Perceptron classifier can classify the following. Which of the gate can perceptron can classify? NOT gate, can it?
XOR gate, sir. XOR.
Can classify XOR and cannot all of them. It is multiple state question. Multiple can classify, multiple cannot. Can classify the following.
XOR and XOR.
Okay, let me go.
Or also.
Yeah, let me go one by one. Okay, so
Sir, A is false. A is false. B, C, D is true.
so NOT gate it cannot do, or and XOR it can do, right? You are saying that. So
Yeah, it's correct.
no, that is not correct. So okay, let's draw a graph. Okay, so suppose this is the graph. Okay, not really. For not, what can be the input? It can be 0. This is the axis. Okay, it can be 0, and this can be 1. Okay, this is 1.
Yeah.
And what would the output? For 0 output.
Sir, 1-0.
So
1,
output,
0.
suppose 1 we are representing with triangle, 0 we are representing with circle.
Circle.
So you can just draw a line here, like you can select this point this point, any point you can choose, and you can separate it, right? So it is separable, right? So NOT gate is linearly separable. Next I'll go to the OR gate. So what is the diagram of OR gate? OR gate is two-dimensional input, right? 0, 1, 1. Okay. Similarly, suppose you are considering a triangle for 1. So 1, 1, if we take OR, what will be the output? 1. Okay. 1, 0, if we take OR, what would be the output? 1.
0.
1 or 0 OR if we take.
Sir, OR gate?
Yeah,
OR?
OR gate, yeah.
Okay, sir. 1 plus 0 is 1.
Yeah.
Sir, 1.
Yes, 1. I have written 1 there, like a triangle is 1. Okay. And 0, 0
Okay, sir.
is like, say,
0.
0. So we can draw a line here and we can still separate it, right?
Sure.
So this is also linearly classifiable. Then let's make another set. Let's draw AND function. 1, 0, 1. So AND 1 and 1 is 1, right? So this is 0, like this is 1. 1 and 0 is 0.
0.
0 and 1 is 0, and this is also 0. 0 and 0. Okay. So we can
0.
just draw a line like this. So this is also linearly separable. So
Right.
NOT and OR, all three are linearly separable. Let's go for XOR. Yes.
XOR.
Yeah. 1, 0, 1. So 0, 0 XOR, what would be the output?
1.
Yes. And no, okay, 0, 1 XOR, what would the 0, 0 XOR is 1.
So it is 1, but for XOR it will be 0, na? So here it is 0, 0 is 0, and it will be for XOR it will be 1. Reverse of OR gate, right?
No. XOR is like for 0, 0 it will be 0.
So you
For
are
1,
saying,
1 also
yeah,
0.
that is not
When
XOR.
it's
You are
a
saying that as a NOR gate, okay? And that is opposite of XOR, OR. So in XOR, if any of the bit is 1, then if one of them is 1, then it is 1. If both of them is 1, or like if there are like odd number, then it is 1. If there are even number of 1, then it is 0. Okay.
If the inputs are different,
Yeah. Input are different, so you can consider like maybe this here. Okay. So it is like input 1, 0 and 1, input 2, 0 and 1. Okay. So if you take 0s or 0, it will be 0. And if you take 1s or 1, it will be also 0. Zeros or 1, it will be 1. And 1s or 0, it will be 1. So can you draw a line to separate them?
No, sir.
Yeah. So that is why it is not linearly classifiable. So there we cannot draw any line to separate those. So it is not linearly separable. So that is the answer to the question. All three are correct, but this one is not. So we cannot classify. So if you have any doubts in the problems, you can ask me. Otherwise, I will end the session.
Will we get in this presentation also? PPTs?
Yeah.
I mean,
I'll share in the discussion forum. So have you joined the discussion forum?
sir.
Okay, you can do one thing. Okay, let me share a sheet where we update everything.
Yes.
So like I will tell to how to find that also. Okay. So you just log in to your NPTEL portal. Okay, then go to there. Okay, problem solving session January 2024. Then
Yes.
go here, problem solving session recording, and we have a sheet here. Okay, you click it here and it will open and you will get everything. So in this folder you will get the slides. Here you will get the recordings for all the TS. Okay, or whoever is taking the
Yes.
yeah.
A lot, sir.
Okay, thank you everyone for joining. So now I will end the session. So yeah, prepare for the assignments and everything. Thank you.
Sir,
Yeah.
sir, can you explain soft margin SVM with the linear kernel and slack variables?
Okay, so I think Sarah has covered that actually. So actually this is a very large topic, so to be covered in this session. So I think you can sit from there, but maybe so. Okay, I'll share you a blog. Okay, so that is written very well. Maybe you can try to find it from there. Yeah, it was their support on
Okay.
SVM. So I'll just share you the link. But I think like if you from exam point of view and everything, if you follow such lecture, it will be better.
Sir, so XOR is
Yes, sir.
not linearly separable, right? All the other functions are.
Yeah, XOR is not separable. All of the other are.
Thank you, sir. It was very healthy discussion, sir.
Thank you very much.
Thanks a lot, sir.
Thank you. Okay, then I'm ending the session. Thank you.
Yes, sir. You can conclude.
Yeah. Okay. Thank you.
Thank you, sir.